Hi everyone. So we've worked pretty hard on the limit definition, and now what we're going to do is work on building up a set of shortcuts. So basically we're going to have a group of functions that we see regularly and some ways to combine functions that we're going to walk through the limit definition and see if we can figure out in general what will happen, and then we'll just use that. Instead of walking through the limit definition every time, we'll use the generality, the rule we created by walking through it. So to get us started, I'm going to look at a couple here. The first one we want to work on is the constant function. So here we're saying c is a constant. It is one value. So it's like a y equals 2 or a y equals 7. And we can figure this out a couple of ways. We can either walk through the limit definition, which I do want to do so you can see it, or we can think about this one graphically because it is a very simple function. Okay, so the limit definition says we're supposed to take our function, which is this thing right here, c, and we are supposed to plug in x plus h first. But there's actually nowhere to plug anything in. Oh, sorry for the yawn. This is f of x equals c, and the way this function works is no matter what you plug in, it always just gives you this number c. So f of x plus h is c, and f of x is also c. And then we're supposed to divide by h. And what we get is that the limit as h approaches 0 of 0 over h is always going to be 0. So this is a rule. So we get our first rule is the derivative of a constant is always 0. So this is the constant function. Okay. Not to be confused with a constant multiplied by something. We'll do that one a little bit later. Okay, yawning again. Next one, let's look at what happens in general. Oh, hold on. Before I move on, I did want to mention the graph part of this thing. If we're thinking about, for example, y equals 7, that's a horizontal line. And remember, derivative means slope. So if we're thinking about the slope of a horizontal line, it is always 0. Okay, so down here, linear function. Once again, this is fairly simple, so we could do it either way. I'm going to show you both. Okay, so first we take our function, which is this whole thing, and we plug in x plus h. X is our variable, so replacing x with x plus h. So there's our function evaluated at x plus h, and then we're supposed to subtract off the original function and divide by h. And there's just a little bit of algebra to be done here. We need to distribute the m and the minus sign. Notice this is not function notation. This is supposed to be m, as in the slope of our function, a number. So we can distribute that through. And then we get to cross some things off. This works out really nicely. The mx's, we can subtract that out, and the same thing with the b's. And we just, oh geez, sorry guys. Too sleepy apparently. We just end up with mh over h. And then if we cancel out the h's, as h goes to 0, all that's left is an m, and nothing's going to happen to that. So we're just getting m. So this is number 2, linear function. The derivative of a linear function mx plus b should always be m. And again, we can think about this graphically. If we have a linear function and we're trying to take its derivative, derivative means slope, so the slope of the linear function is staring right at us in the equation. It is that m, so we should expect to get that. Okay, and now I want to change gears just a little bit. The rest of this is to work our way towards a pattern for power functions. So now that we have the linear function rule, we want to, let's see, figure out the derivative of plain old x. So this is really just a special case. This is a linear function, y equals x, so the slope is 1, which means the derivative will be 1. And what I'm doing in these last few parts is just giving you a couple of examples, not a lot, but a couple, to build up a pattern and see if we can figure out what the power rule is. So C and D, should say, oh, no, it's okay. C and D, you can pause and work through on your own if you'd like to, and get a little bit more practice in with this limit definition. I'm just going to zip through them really quickly. So if we want the derivative of x squared, we're going to plug in x plus h, and then we're going to subtract the original function, and we're going to divide by h. So this will give us the limit as h approaches 0. So we'll need to FOIL that out, which will give us an x squared plus 2xh plus h squared minus x squared. And we get to cross out the x squareds, and we get to factor out an h. And then, oh, yet again, all that we're left with is 2x plus h, and as h goes to 0, that means that we're just going to get 2x for that one. So we've gotten the derivative of x is 1, the derivative of x squared is 2, and now we want to work on the derivative of x cubed. Okay, so we need our function evaluated at x plus h, which will be an x plus h cubed, minus the original function x cubed, and all that should get divided by h. Okay, and this gets a little bit tedious, and that's why I'm wimping out at x cubed and not going on to x to the 4. I would really like to quit yawning, but apparently it's not going to happen. Okay, so this is an x plus h times x plus h times x plus h. And you can pick a pair, say the first two, and you can FOIL them out. It's exactly what we did before. And you'll get x squared plus 2xh plus h squared multiplied by an x plus h. And then you have to go back to what FOIL really is, which is distribute. You're going to hook together, it doesn't matter which one, but I'm going to distribute the x plus h through and multiply it by each of those three terms. So you'll have x squared multiplied by x plus h. When we multiply x squared by x plus h, we get x cubed plus hx squared. And then we'll have 2xh multiplied by x plus h. So when we multiply by the x, we get 2hx squared. Sorry for changing order. I'm just trying to be consistent. So I started with h's first, and I'm going to stick with it. And then when we multiply the h by 2xh, we get 2h squared x. I'm going uphill. And then, where am I at? Okay, h squared has to get multiplied by x plus h. So the x times h squared is h squared x. And the h times h squared is h cubed. And all that should be divided by h. Okay, oh, and I lost one, minus the x cubed that was there originally. So now we get to do a little bit of cleaning up. The x cubes go away. That looks like all that goes away, but we do have some like terms. So the hx squareds can be combined. I have 3 of them, 3 hx squareds. The 2h squared x and h squared x are like terms, so I also have 3h squared x's. And then I have an h cubed. Okay, almost done. Maybe it's good that I was going uphill. The limit as h approaches 0. Okay, so if we factor out an h, we'll have 3x squared plus 3hx plus h squared. And then we can cancel the h. And as h goes to 0, this 3h squared will go to 0. Or I'm sorry, the 3hx will go to 0. The h squared will go to 0. And all I'm left with is a 3x squared. Okay, so again, I'm wimping out here because I don't want to have to multiply an x to the 4th out. It's doable, but kind of tedious. I am still yawning. And I am going to try and look for a pattern a little bit here. So what I see is the thing I was taking the derivative of is an x squared, and x cubed, and I'm trying to guess what will happen for x to the 4th. So what happens is your power increases, basically. And one thing I see is that the constant goes 1, 2, 3. So I'm going to guess that this will go 4, 5. And then the variable, the first one doesn't have a variable, but remember you can think about that as an x to the 0. So the variable, the power goes 0, 1, 2. So I'm going to guess that this is a 3 and this is a 4. And if we try and generalize the pattern we're seeing there, we end up with the power rule, number 3 for us. X to the n is n x to the n minus 1. So whatever the power was, it ends up out in front, and the new power is 1 less than the old power. So this is the power rule. Okay, and the idea is, as soon as I give you these, give them a name and a number here, you can use them for free. You no longer have to go back to your limit definition to take the derivative of, say, x to the 6th, or x to the 1/2, or x to any power. All right, thanks.